All right, so we are doing Java 4 lesson 8, and I have a big 8 up there because it is the last lesson of all of the Java series that you have gone through. Congratulations for making it to this day, because Java 4 lesson 8 is the last lesson of like the whole Java series. And so after you're done with this, then you're probably just done for the rest of your time, unless you decide to come back and learn something again, or if you want to come back and teach, that's another thing. But besides that, you're going to be done. Or if I like implement something, another course, which I might. But anyways, that's something for later. But this is the last lesson. And we're talking about efficient sorts today. Okay, I also took the liberty of adding some images for your viewing pleasure. Okay, so if efficient sorts are efficient, but they can be hard to code. And I do have to note that I'm not going to teach you how to code them necessarily. The only thing I want you to know how to do is essentially just know how they work and how to sort an array using that particular method. And so this should be a relatively easier lesson as long as you get what the sorts are actually doing. Because we're not going to do any code today. I think I might implement some coding parts later, but not right now. And you don't have to know that for the test. So yay. Okay, sorry, readjusting my screen because it's not working. Okay. All right, the first sort we're going to learn about is merge sort. This essentially continuously splits everything in the array into two until everything is in a subarray on its own. So like everything is one by itself. So if we had 5 elements within an array, we would continuously split everything into 2 until all of the elements are in separate subarrays on their own. Then essentially we will just order, or like essentially just swap the values if they're not in order, the subarrays while we're merging them back together. So while we're merging the subarrays back together, we're going to check to make sure that all of the elements are in their correct placing. If they're not, then we swap the 2 and then continue to sort until you finally end up with a final array that is completely sorted. And yeah, so you usually have 2 arrays. One is the current array and one is the final array when you're implementing it. The reason why you have those 2 arrays is because you can't override a current array. Otherwise, you'd be like deleting some values or like you're missing some values due to overriding the array. So what you need to do is you have another array to store the values first while you're ordering, and then you override that current array and return that array. So that's usually how it goes. But again, you don't really have to know how to implement this. It's just like for your information, this is what it does. And also it's the fact that you have to create another array, which means you have to have more storage because you have to store more elements. So yeah, you just want to know this. I'm not going to really test you on it, but it's a thing to know. All right, so a drawing, of course, we need a drawing for all the sorts. And I apologize, it's kind of loud over here. But yeah, if we have an array 3, 1, 4, 0, -2, what we want to do, right, is split everything into 2 first. So what happens is that I'm going to start splitting. So yeah, usually it's something like this. It might not be completely like this, but something like this. Sorry. Okay. Okay, so we're splitting everything into 2, right? So what happens is that I split 3, 1 into one array, and then 4, 0, -2 into another array. And then again, I completely continue to start separating them. So I do 3 and 1 are now on their own. 4 is on its own, but then we have 0 and -2 because we're splitting 3 elements into 2 arrays. And lastly, we get to a point where we have all of them in single arrays. You can see that every single element is within their own array. And then we start merging them back together, which again, like merge sort. So for example, when we first merge 3 and 1 together, we order them. So we do 1 first and then 3. 4 is still on its own, but we can see that when we're ordering 0 and -2 together again, -2 and 0. So we're like ordering them while we're merging. We then merge 1, 3, and still merge together. We merge 4, -2, and 0 together. And I sort them when I'm merging them. And then after that, I finally merge them into one gigantic array like it was originally. And that you will see we get -2, 0, 1, 3, and 4. And that's all sorted. Good question. And the question was like if 4 can go on left array instead of right array for the purpose of the recording. I think like it depends on how you're gonna partition it, which means like how you're gonna split it apart. You can do it, you can move it in, but because on the test, I'm gonna have a section where you have to like manually sort these arrays, like without using sorting methods. But well, like you're using a sorting method to sort the array, but you're not gonna use code for it. You're just gonna manually sort it. For that particular part, I would accept either one. Like you could put the four in the left array and that would still give you credit, or you can put it in the right array. It doesn't really matter to me. But if you have like an even number of elements and then you just have 3 in one array and 1 in the other, that's not what's going to happen. And then I would mark you off. But for like odd number arrays like this one, since it's 5, then yeah, I wouldn't mark you off if you wanted to put the 4 in the left array. Good question. Yeah, it's generally like this. The code can differ and then it will depend on what you do, but this should be fine. But yeah, the main thing for merge sort again is you split everything apart into its own individual parts. And then we systematically go back through and we're starting to merge them together and order them while we're doing that. So it's an efficient sort because it uses recursion. Remember recursion? That was like the thing we learned in Java 4. Yeah, we're using them again. But again, you don't need to know how to do that. I'm just saying that it uses recursion, which means it's really efficient with doing this. Okay, doke. Again, I'm not going to go through the code, so we're going to just move on to the next one, which is quicksort. So firstly, for quicksort, you have to choose a pivot. So I'll explain like exactly how you choose a pivot, but essentially a pivot's kind of just like a place where we are basing all of our elements off of. So like, yeah, we just choose a number in the array to be a pivot so that we can base other elements off of that. We have a pointer named low and a pointer named high. And by pointer, I kind of just mean like a variable that points to that index. So like, it's not anything special. I just call it a pointer, but essentially it's just a variable that points to a particular index. We have these pointers, and what we do is that they start at different ends. So one of them, particularly the high pointer starts at the very end of the array, and low starts at the very start of the array. So we have those pointers that point to there. Then what happens is that the high pointer, which is at the end of the array, tries to find a number lower than the pivot. And it continues decreasing down the array until it finds one or it reaches the low pointer. So yeah, essentially like the high pointer is trying to go down the array like this until it finds something that's lower than the pivot. Sorry. The low, which is at the start of the array, tries to find a number that's higher than the pivot. And it continues increasing up the array until it finds one or it reaches the high pointer. And so yeah, it continues going up. The point of why we're trying to do this is so that we find numbers that are out of place within like the respective ends. And then we essentially just swap the low and high. So particularly the numbers that are associated with that particular index, not the pointers themselves. So we swap the elements that are at those particular positions if they're out of place, right? And then we just move on to the next element that pointer's respective path, right? So after we swap the high pointers values, then we move on to the next one that's below it, all right? And then if we just swap the low pointers values, then we move to the one that's immediately after that. Hopefully that makes sense. But essentially, you continue doing that until the low pointer's position is equal to the high pointer's position. Because then like we're done with sorting the array. We are done with checking to make sure that everything's in the correct place. And so we don't need to do this anymore. So what we do is we decrement the low pointer's position by 1. And then we just swap the pivot element, whatever it is, with the low variable, like where it was. So we swap the elements at the pointer, the elements at the pivot and the element that is at the low position. And that's essentially how we sort that. So essentially it's kind of like the pivot's supposed to be the middle element, and we are just sorting everything on the left and right parts of the where the pivot, right? To make it so that everything lower than the pivot is to the left of the pivot, and everything that is greater than the pivot should be to the right of the pivot. And I know this kind of seems confusing. I think it's a lot more confusing than merge sort, but yeah, I have like diagrams, and I also have a video to show you guys that explains a bit more about it in a visual manner. Yeah. Quicksort then again recursively sorts the left and right array using the same method until they are sorted. So essentially, after we place the pivot where it's supposed to go, then essentially we, in the left array, we choose another pivot that we're going to base the whole thing off of, and then we start sorting them again. So using the low and high pointers again to start swapping elements until they're all sorted, and then placing the pivot where it's supposed to go. In the right array, we do the same thing. We start picking a pivot, we have the low and high pointers in the right array, and then we start swapping until we get to the point where we can put the pivot in, and then we're done. And again, we continuously sort these parts until everything is sorted. So yeah, again, this is faster than merge sort, but it's also more complicated. So it does get a bit hard to understand sometimes, and also hard to code, but it is faster than merge sort. So that's a good thing. And then, yeah, but generally it uses recursion as well as merge sort. So part of the reason why it's a bit more complicated, but it is more efficient. So if you wanted to sort like really large data at like a really small amount of time, then usually you want to use quicksort or merge sort. And I kept talking about the pivot, like I didn't really explain like how you choose the pivot, like what exactly it is. And essentially, a good way to set a pivot is that the pivot should be close to the median. And what I mean by the median is like the median of their array. So, okay, let's do a quick poll here. Give me a 0 in the chat if you have not learned about medians yet, or give me a 1 if you have learned about medians in your math classes. No, Tony, median in your math classes. So 0 or 1. 0 for no, 1 for yes, that you have learned about median before. Okay. Yeah, so you guys should know pretty well, but essentially, again, just to recap, you're kind of just ordering all of the elements in the array and picking the one that is closest, like in the middle, right? And so that's essentially what we're trying to do here, just to make it so that we're actually sorting the arrays. And so, yeah, we should try to pick one that's close to the median. And a good way to do that, right, is to take the first element of the array, the unsorted array. We take the last element of the array, and we take the middle element of the array. And then essentially what we do is we compare them, right? We compare the 3 elements that we picked out, and we find the median of those. So whichever one has a middle value that is between the other 2, then we're going to choose that one as the pivot, because it's more likely to be the median of your whole array. And so therefore we should be choosing that particular middle value to be our pivot, because that way we are sorting the most elements, right? Because then we have a pretty good partition of the array. So like everything that is less than a pivot is over here. Everything is more than the pivot is over there. We're sorting everything a lot better, and we're making sure that the halves are mostly equal to each other, like in terms of how many elements are there, which makes it a lot easier, and it makes the quicksort more efficient. Because otherwise, like, yeah, if you choose something that's like supposed to be at the very front of the array, then you're not really sorting anything at all. Like you're keeping mostly everything the same as it is, so it doesn't do anything. So the point is to like continuously do that so that you're doing the most amount of work in the less amount of time. So yeah, if necessary, and if you just don't have the time to code anything better, then you can just take the first or last element of the array and just say that's the pivot. But that's generally not the best way because again, efficiency can vary. Because like, okay, well, sometimes the first element of the array, like the very first one at index 0, that might actually be the median of the array. But you don't know, right? It could also be the least element of the array, or it could also be the largest element of the array. We don't know, right? So usually it's better to do some comparing first and compare the first, last, and middle element to see which one's like closer to the middle. So that way, at least you don't get the largest element of the array or the lowest element of the array. So yeah, usually you want to compare the 3 elements first. All right, and a drawing. So yeah, fortunately it's kind of hard to see, but what happened here is I kind of just chose the first element of the array. It's not the best thing to do, but also like if you see here, if we look at the first element, which is 3, second element, which is last element, which is -2, and the middle element, which is 4, we do see that the 3 is between the 2, right? Because 3 is between 4 and -2. So it's actually pretty good for a pivot. So we're just going to stick with that for now. But essentially, we keep the 3 there. And again, we have the 2 pointers that help us figure out what we're doing. The low is pointing to the very first element after the pivot. And the H is going to the very top one. And just a note, I forgot to mention before, but the pivot should also always be the very first element so that we don't count that when we're sorting. And so, yeah, usually we want to move the pivot to the very front of the array to swap it with whatever is in the very front of the array. Forgot to mention that, I apologize. But yeah, and then what we want to do, right, again, have the pointers, but then we want to compare, right? So we want to see, okay, is this current pointer that is pointing to, is the value less than the pivot? Well, then yeah, it is less than the pivot, right? Because 1 is less than 3 still. So we're not going to consider it because we don't need to swap that. That's already in place. So what we do is we move on to the next element. Okay, and then we're at 4, right? So we see, okay, well, is 4 less than 3? Well, no, it's not, right? So what we do is we found an element that is out of place because it's not supposed to be there, right? The low is supposed to keep track of whichever element is higher than the pivot. Over here for the high pointer, we're asking over here whether the element it is pointing at is less than the pivot. Well, in this case, yeah, right, -2 is less than 3. And so it is also out of place because the high variable is keeping track of whichever ones are not supposed to be there, which in this case is things less than the pivot. So what we do then is we swap the 2 because they're not in place. And so we need to swap the 2. So what we do, we put -2 here and 4 over here. But then what happens, right, is that we both move on to the 0 element. And we both find that, yeah, this part's drawn wrong, but essentially what happens is that the high pointer moves down to the 0. And the low pointer also moves down to the 0, up to the 0, sorry. And so therefore, since low is equal to high, then we're done with that particular array. What we do then is we decrement the low by 1. So we go down to -2 for the low. Or, yeah. Okay, this diagram is drawn wrong. I apologize. Yeah, you're supposed to decrement low by 1. You're going to go over here to this part. And then essentially you're just, I believe so, right? Maybe. Anyways. Yeah, essentially you would just put 3 where it's supposed to be, which is over here, which is like 1 below the 4. You partition it into 2. And then depending on that, you're going to recursively sort each half. So what you do, you pick a pivot, you sort it, and then you pick another pivot and over here, and again, you're sorting that. So again, you're implementing your own low pointer and high pointer for each part of the array. And again, you're just sorting that again to get this. I didn't put all the parts, which again is probably this diagrams part. I need to readjust the diagram then to fully sort it out. But I hope you guys get the process, sort of. Is this all kind of making sense so far? I feel like I've just made this more confusing with the diagram. Scale of 1 to 10. Okay. Alrighty then. Okay, so like I said, I had a video that I thought was pretty good at demonstrating, like just generally. Give me a second. But yeah, I thought this video was pretty good at explaining it and had like an animation to it. So I wanted to show it to you guys. So we're gonna take a quick pause, or not a quick pause, but you guys are gonna watch this video and they will kind of like using because they will explain. Let me change the sharing settings so that. Okay, you should be able to hear sound now, but let me know if you can't hear the sound.
Hi, I'm Joe James, and in this video I'm going to explain the quicksort algorithm, and then I'm going to show you how to implement quicksort in Java. Given an array of items, we want to sort them in ascending order, and that's what quicksort does. In this video we're simply going to use integers for our items to keep it simple, but you could actually sort any item that's comparable. So here we have an array of 9 items. First we need to explain some terminology. We have a pivot. A pivot is an item that we're going to compare every other item to. We're going to move items that are smaller than the pivot to the left of the pivot, and items that are greater than the pivot to the right of the pivot. After we've done that, we're going to have a left partition and a right partition. So let's go ahead and sort this list. We'll apply quicksort to this list of 9 items. First we select a pivot. We've chosen 13 as our pivot. That's item number 8. So we'll start from the left and we'll say, is 17 greater than our pivot? Yes, it is. Now we'll start on the right. Is 3 less than the pivot? Yes, it is. So we'll swap those 2 items. We do a swap. We're going to move both pointers in. We'll start at the left again. Is 41 greater than the pivot? Yes, it is. Is 29 less than the pivot? No. So we move that pointer over. Is 6 less than the pivot? Yes. So now we know that we can swap these 2 items. We'll move both pointers in again. Is 5 greater than the pivot? No, it's not. Is 22 greater than the pivot? Yes. Is 54 less than the pivot? No. So we move that pointer over and look, the 2 pointers meet in the middle. Lower and upper indexes meet. We're done sorting around this pivot. What we can do is simply swap the pivot in for the lower index. So we want to swap the 22 with our pivot value, the 13. Now we know that all the items to the left of the 13 are lower than 13. All of the items to the right of 13 are greater than 13. So 13 is in the correct position now. So we have a left partition and a right partition. And we're going to call quicksort on each of those 2 partitions. So on the left partition, we'll choose a pivot value. We'll choose 5. We're going to compare, is 3 greater than the pivot? No. And our indices have met already in the middle. So we can swap the 5 in with the 6. And now the 5 is in its correct position. And we have a left and a right partition that consists of only 1 item. So we have to assume those are already sorted. So now the left partition from the 13 is fully sorted. Now we have a right partition with 5 items in it. First let's choose a pivot, 22. We'll compare 54 to 22. Is 54 greater than the pivot? Yes, it is. Is 17 less than the pivot? Yes. So we can swap the 54. Now we can move both pointers in. Is 41 greater than the pivot? Yes. Is 29 less than the pivot? No. We move that pointer down and both pointers meet in the middle. Now we want to swap our pivot value with the 41. Now we know the 22 is in its correct position. We have a left partition that consists of only 1 item, So that's sorted. And we have a right partition that we need to call quicksort on. So we'll choose a partition, 41. Is 29 greater than our pivot? No, it's not. And our indices have met in the middle. So now we can swap 41 into the position with the 54. Now our pivot 41 is in the correct position, and its left and right partitions are both already sorted because they only consist of one item apiece. So the list is fully sorted. That is how quicksort works. Quicksort is a recursive method. It's a method that calls itself because it continues to call quicksort on a smaller and smaller subset of the items. It's also called a divide and conquer algorithm. It's very efficient for very large data sets. The worst case for the quicksort algorithm is...
You don't need to know this, by the way. Like, this is analysis part, and I never tell you that, so you don't need to know this for the test. So just so you know.
Big O. Performance of L source, which may not be the best. How to pivot is going to result in big O of n squared performance. So how do we select a pivot? Well, you can choose the first item in the list, which may not be the best choice, or the last item in the list, which also may not be the best choice. Those are bad choices because if you want to either forward sort or reverse sort a list that is already in sorted order, you could get worst case performance by choosing the first or last item in the list. You could also choose the middle item in the list. That will usually give pretty good performance. Or you could choose middle of 3. So you could look at the first, last, and middle items and choose the middle, the median of those 3. But randomly chosen pivots ensure big O of n log n performance, at least for large lists. Now let's take a look at our Java code.
Okay. I'm not going to teach you on the random part, but I think you guys should be able to do it anyways. Like, you would essentially just kind of do math.random, sort of, like to find a random pivot if you wanted to. But yeah, you don't need to know the code, but it has the code here if you want to look at it later on your own time. But I think the major things to get from that is, again, that like we're recursively sorting and we're finding pivots. We're comparing these like low and high pointers, and then we're continuously trying to find the point where we need to swap the two elements at the low and high pointers. And lastly, kind of the last notes. For arrays with 7 elements or less, usually just about that number, I would suggest using insertion sort, selection sort, bubble sort, etc. Just because, like you've seen the code before, it does seem kind of like unfamiliar, sort of. It is a bit like complicated for these sorts, but like merge sort and quicksort, they're like kind of even complicated, more complicated. But if we're comparing like these, like as you have more and more elements inside of arrays, then it gets harder and harder and more time it takes for insertion sort, bubble sort to like actually get the elements sorted. So usually if you want to save time with coding and you also like are not sorting a very big array, then use something like insertion sort or like the inefficient sorts. And otherwise use quicksort and merge sort, because if you have like large arrays, again, you would want to sort things in as quick time as possible. So usually it's a good thing to do this. Besides that, remember that we also had the visualization tool for more visualizing on the inefficient sorts. They also have it for merge sort and quicksort, so you might as well go take a look at it. Escape. Okay, let's do merge sort first. So again, remember that merge sort is when you're splitting everything into 2 and then you're merging them and sorting them as you're merging. Yeah, I think it's right. It's like they already sorted it all by the color scheme. And the way they're kind of like going through it and matching things is the way they would be sorting them. if that makes sense. So like they already color sorted it by the colors. And they're just in the process of like merging things back together by like combining colors, if that makes sense. So yeah, see how they're like comparing the 26 and 36, and now they're going to compare the yellow elements with the green elements. You can see how they're all sorted now, and then you just put it back into the array. And now they're going to compare the 2 and the 27 now, or never mind. That goes first. But again, see how they're like comparing each element to see which one should be going next. 44 now, and then 47. And now they're going to sort the right part of the array. And you can see again that now like the left part is completely sorted. And then again, it does the same thing for this part. Continuously sorts them, matches them to their color. They're going to compare 46 and 4 now and order it before putting it back into the array. It's going to sort 2, 4, 27, and 46 now. Copies them back into the array. It sorts 19, 50, and 48 now, or more like 19 to 50 first. And then does that, add in the 48. And then again, like it merges everything back together for the both parts of that. Puts it back. And then now what happens again is that now that we sorted the left part and the right part already, you put them all together back into the original array by sorting through each of these. And then they just copy it back into the array. That takes it. But yeah, then it's all sorted. Scale of 1 to 10, does this kind of make sense? So like, again, they already split it by the colors at the beginning, but then they're like doing it step by step, combining the ones adjacent to each other first, and then continuously merging them into larger and larger sections. Nice. That's a good number. All right, so yeah. Again, you can like look at this later, and I think you can also, yeah, you can also like change up what the things are and see like what would happen if it's sorted or nearly sorted, that kind of thing. Or we can go into quick sort. So again, this takes the pivots and then it continuously compares the low and high pointers continuously until it swaps everything, puts the pivot back where it's supposed to be, and recursively sorts the left and right half of the arrays. So let's move this slow first. So choose number 3 as the pivot first. This particular sort, it kind of marks in purple what the higher elements are. And if it finds any lower elements than 3, then it marks it in a different color. So you can see they're purple. Oh no, 2 is not there. It is less than the pivot. So it continuously marks things that are higher and just leaves it there. This is kind of like another way to do it, but we're going with the way I was teaching it. At the end, it just swaps things to put the pivot where it's supposed to be. We find 38 to be our new pivot because that's like still the right half of the array and needs to be sorted. And you can see that the green elements are the ones that are less than 38. Purple elements are the ones that are greater. if we find anything that's not in place, we swap it to where it's supposed to be. AKA if it's less than the pivot, then we swap it and move it there and mark it green. And yeah, once we have those parts, then we're able to put 38, which is the pivot, where it's supposed to go. We mark it orange because it's already sorted. We choose 19 as our new pivot. And again, we continuously mark it again. So if it's greater, we mark it purple. If it's less, then we mark it green, and then we just move it where it's supposed to be with the other greens. We move 19 to where it's supposed to be. 19 is sorted now. And now again, we're just gonna partition it again. We're gonna have it again, and we're just gonna continue doing that. Find that 4 is where it's supposed to be. Find that also 5 is where it's supposed to be. 15 is automatically there because, like, again, if it's a single element, like the video said, we just don't need to consider it again because it should be already sorted. And yeah, it kind of continues going through the halves. Oops. Now that we sorted that part of the array, then we get to the other part. Choose 46 as our pivot. And again, we are marking things green or purple to decide whether it's less than the pivot or greater than the pivot. Move the pivot where it's supposed to be. Mark that as sorted, and then we go back. I'm gonna move it up in speed. Swap it. And then we're done. So yeah, it's again, like the merge sort, we're continuously searching each half, finding the pivot, finding whether certain elements are less than the pivot or greater than the pivot, and we're making sure we're keeping track of that. If they're not in place, then we swap it so that it is in place in terms of like less than the pivot and higher than the pivot. At the end, when we're done sorting all of it, then we place the pivot back where it's supposed to be in the middle of those two halves. And then we sort the left half, sort the right half. How much does this make sense on a scale of 1 to 10? Alrighty, sounds good. But yeah, it might take a bit to still get familiar with this. And again, you can play with what you can do. So you can like vary up what elements you're doing. So that should be fun. Yeah, besides that, we're actually done with the lesson, and we are actually finished before the end of the class today. Wow. Okay. So again, you do not need to know any of the code for this. You do not need to do that because I'm not going to test you on it. So if you want to learn though, you can search it up. And the video also has the example of quicksort. All right, but again, the main thing you need to know is how to sort elements. So that's essentially what I was planning on doing for the rest of the class today, which is essentially just, I'm going to give you an array. I'm going to tell you to sort it using merge sort or quicksort. And you have to like sort it all using the various methods until you arrive at your final answer. You do have to show me exactly like how you got that to the answer though. So for example, if we're talking about merge sort, then you should show me exactly what's being partitioned, right? So like you should be telling me, okay, if we had this element right here, yeah, let's go with that first. If I gave you this array, oh wow, spacing's off. No, okay. So I give you, if you guys using merge sort, if I give you this array, then by each step, I mean that you should show me what's happening. So you should show me that we're doing 5, 2, 9 in one array. You should also show me 6, 0, -1 in the other array. And then you would also have to show me how to partition it even further. So you have to show me like 5, 2 in one array, and then 9 in the other, and so on and so forth, right? So you would show me again 6, 0, -1. Okay, That's what I mean by each step. You have to show me each step of the way. If we're partitioning it, if we're having it, and then you also have to show me each part where we're actually merging it together. So that's kind of what I expect when I'm asking, okay, sort this using merge sort. You have to show me each step of the way and write out what the array looks like so far when we're doing this. All right. So yeah, I have started the first one for you. Your job now is to finish it. That is your class problem. And when you're done with that, we can do the same thing. But now using quicksort. And for quicksort, what I expect you to do is mark out what your pivot is. Like you have to show me, you have to write, okay, my pivot is value. Okay, you can't just continue sorting. You should tell me what your pivot is and what your low index is at and what your high index is at. That's what I expect for quicksort while you're switching it. So that's what I expect for both of them. And for the rest of the class, we are going to be doing it. And I will also share the lesson slides with you in the chat. All right, but that should be pretty much it for today's lesson. We're just going to be doing that, and I'll be going over the answers at the end.